So, Bob, by the late 1980s, your work changed from alloys and kind of working with melt spinning and in phase equilibria and titanium alloys, and it changed in a very what on the face of it seems like a very radical way to looking at high temperature ceramic superconductors. It seems like a real significant pivot. How does that kind of connect to these other topics? How did this work kind of originate for you?
Well, it came out of the fact that um, after working on these other two projects I described earlier, the melt spinning and the phase equilibria, one of the things I found when I was at NBS is that there was no magnetism activity per se at this place. And of course, having been trained in that area as well as materials science at University of Illinois, Champaign-Urbana, I was interested in perhaps starting some activity in that area. And there were two other individuals that I had met in this interim period at NBS who also had a magnetism background partially, but from different directions. And they were a fellow named Larry Bennett, Lawrence H. Bennett. He he had done a lot of work in nuclear magnetic resonance. In fact, his work doing an NMR probe of a cancer in a rat's tail that was cited by the individual who ended up receiving the Nobel Prize for developing magnetic resonance imaging. And a second person was Leiden Schwarzendruber. He was an electrical engineer by training, but had done a lot of Nussbauer spectroscopy. And so the three of us went to the laboratory director at that time of our laboratory, the Materials Science and Engineering Laboratory, and suggested we start a group probing magnetic structure, magnetic properties of materials. This laboratory director was Lyle Schwartz. He had come to NBS from Northwestern University, where he was a Nussbauer spectroscopist. So he appreciated the significance of being able to measure magnetic properties of materials. And so he was very receptive to this idea and said he would talk to our division chief about seeing how they could do this. And so they freed up a little bit of money for us to get started. So I kind of left this these other two activities and started this new group of magnetic materials. Now, there was only enough money to purchase one piece of equipment, and so we purchased a magnet, an electromagnet, and we purchased a vibrating sample magnetometer designed after the design of Cy Foner at MIT. And so this was the only tool we had at our disposal, but it was sufficient for us to get started. And so we started to make some magnetic measurements, and I got into fine particle magnetism as a consequence of this. So I started looking at the types of characters you would create when you made thin films by sputtering. In fact, co-sputtering two different species together, and you'd form a kind of a mixture of materials in a thin film form, and I was probing this magnetism of it. Shortly after, like a year or so after we had gotten started with this new group and measuring magnetism, magnetic properties, there was a discovery by two scientists in Switzerland, Bednorz and Mueller, And they had discovered this high temperature superconductivity that was available in some ceramics. And this was not the first ceramic, of course, that showed this, but it was the first ceramic that showed superconducting transition temperatures as high as 40 degrees Kelvin. And some of these lanthanum, strontium, copper oxide was one of the first ones that they came out with. And then later on, Paul Chu discovered superconductivity occurring up as high as 90 degrees or 92 degrees Kelvin in a yttrium, barium, copper oxide. Well, these discoveries stunned the world. The whole scientific community was stunned by these discoveries. And most of us stopped what we were doing and went into the superconductivity area to see what we could do to help explore how such a phenomenon could occur in these unusual oxides. And because up till then, and primarily in metals and alloys, but this was kind of a new class. And so that's how I kind of moved in that area. And everybody was working full blast. I mean, it was a terribly exciting time in the physics and materials community who were working in electronic or magnetic characters of these materials.
There was a very famous APS March meeting where the announcement came out, and it went deep into the night. Were you at that meeting?
So indeed, I was there. It was in New York City. It was the well-known March meeting of the American Physical Society, this was in 1988, March of 1988. And I was present at this meeting, presenting work on my co-sputtering of iron and silica, as I recall, combined at this meeting. And it was like the Woodstock of physics. I mean, everybody was excited. They held a special session in the evening of this one day. I think it was the second day of the meeting, and the session was going to start at like 6 o'clock in the evening. By 5 o'clock in the evening, this whole hotel convention, it was in a hotel, all the space, the meeting rooms and everything was completely filled up by people sitting on the stairwells in order to be able to view these closed screen TVs they had set up outside of the meeting room, because you couldn't get in the meeting room, which would house easily 1,000 people. You couldn't get in there, it was so packed. It was just terribly exciting. Well, the meeting went on until, I don't know, 3 or 4 in the morning. I remember I was able to finally get into the actual room, the actual meeting room, at about 1 o'clock in the morning, and I lasted for another hour in there. And then I decided I had to go to bed. Anyway, it was amazing. I've never seen anything before like that in the scientific community or even afterwards. So this kind of showed the excitement and enthusiasm of the whole physics community around the world.
So was it an influence on what you did for your contributions to this area? Did you learn some things that kind of gave you an idea, a spark for your contribution?
So indeed, I think most of us then went to using the tools that we had at our disposal and our expertise to utilize it in probing these new materials. Well, the one thing I was doing, as I mentioned, was doing this co-sputtering of thin films. And I remember this paper by William McLean. I think he was at Princeton. I may be wrong there, but before this time, on discovering or probing the superconductivity in aluminum and aluminum films. And when you made particulate aluminum films, then the superconducting transition temperature rose in aluminum. it went up to, I think, maybe 4.4 degrees Kelvin from 4.1 degrees Kelvin, something like that. It wasn't a monumental increase, but it increased it by having this film of aluminum particles. So I thought, that's what we can do here. That's probably where this high temperature superconductivity comes from in these yttrium, barium, and copper oxides, is because of the particulate nature of it. So we'll do some sputtering, we'll do some co-sputtering, make these small particles of the yttrium, barium, copper oxide, and also lanthanum, strontium, copper oxide, and we'll get transition temperatures which are up to room temperature. So this was my thought. Showed how naive I was, of course. So see, I was collaborating at this time to do this co-sputtering with a group at the Applied Physics Lab of Johns Hopkins University. The well-known APL, Johns Hopkins University Applied Physics Lab. And with Kishan Morjani was this professor or this fellow scientist's name. So we tried sputtering, and it didn't work. Didn't work at all. So we did this like 2 days after this APS Woodstock in New York City, and it didn't work. And so then we decided to try using another tool that Kishan Morjani had in his laboratory. I've never utilized it, called a laser ablation system for making thin films. Here you send a laser hitting a target of the material you want to deposit into a thin film. It blasts the material away from this target. It then deposits on some sort of substrate, making your thin film. So we tried that, and it worked. And it worked. We say it worked because at the same time, Kishan Morjani, he also was a NMR specialist. He had this system for doing NMR, but he came up with this idea of modulating a magnetic field on top of the sample at a slow rate, and you look at the absorption of the microwave in this system in phase with this slow field modulation. The idea here is that when a superconductor changes from superconducting to normal, it will do that as you apply a field to it, so its transition temperature will modulate in phase with a field modulation. And so if we measured the microwave absorption in phase with that, we could detect a superconducting transition. So that's what we applied to these thin films. And sure enough, we could see a nice big signature at what we thought was the transition temperature, which was right around that of both yttrium, barium, copper oxide, and similarly for lanthanum, strontium, copper oxide. So that's how we got into it. So we wrote up the paper, and by the end of that week, we had submitted this paper. We got it through the review process at the NBS, which is unheard of in that short of time, and sent to Phys Rev letters for publishing. Well, that get held up for a couple of months before it got published, and in the interim time, there were other announcements of other discoveries of making thin films by laser ablation. That turned out to be the method of choice industrially after that. So that got us into it. But in the meantime, I started doing some other things. And in particular, this friend of one of the co-discoverers of the yttrium, barium, copper oxide superconductor, a fellow named M.K. Wu. He had been a student of Paul Chu's at University of Houston. He was at this time now a professor or assistant professor at University of Alabama in Huntsville. And he had come up with a variation of this yttrium, barium, copper oxide material. Basically, he added some silver to it, making it kind of a composite, kind of like what I was doing before, but not with those materials. And he gave some of this material to a friend of his named Chaoyang Wang. He was a member of the scientific staff at Lockheed Corporation in California. Anyway, this fellow Xiaoyan Wang, brought this sample to our lab and said, look, this has an unusual effect that you can attract this superconductor with a magnet. Of course, we told him, go away. We have many more important things to be doing now, probing these materials. That's not possible. We all know that a superconductor repels a magnet because of the flux exclusion of the magnetic field by the superconductor, creating supercurrents in the superconductor that creates an image of the magnet that's outside of it. So you have two similar poles close to each other, and that repels. You can't attract it. So we told him, go away. Well, he didn't go away. He came and he demonstrated this. He had a little magnet, bar magnet. He put it close to the superconductor that had been made in M.K. Wu's lab in Alabama. And he pulled this magnet away, and sure enough, the superconductor came with it.
But it wasn't touching it.
Attracted, but it wasn't touching. It stayed stably located below it, and we couldn't believe it. So then we began getting interested, and we put some of this material into our vibrating sample magnetometer that we had, okay, and we measured a hysteresis loop, magnetization versus field of it, found it was a typical type 2 superconductor, which means it has a very broad open loop, and realized that indeed in the operating region in the where you have a positive field and positive magnetization, that as the superconductor gets further away from the magnet, then the field decreases, but the attractive force increases, because in a type 2 superconductor, you've got some magnetic flux trapped in the superconductor, and it's like a permanent magnet at the same time as having a superconductor. So you have both repulsive and attractive forces. And in this particular case, you could get stable levitation. So it was really a learning experience, also quite fun. And we then published this and performed all sorts of demonstrations showing that, our general concept was of attraction and repulsion in superconductors is not complete. And this, of course, showed that even the old type 2 superconductors that were well known at very low temperatures should exhibit exactly the same phenomena. But of course, nobody ever tried to measure that, because you had to do this under liquid helium conditions, not at liquid nitrogen conditions of these high temperature superconductors. And so people went to check that out. Sure enough, found it in the old type 2 superconductors. And then the third thing that we did was there was another scientist at NBS, a fellow named Alan Melmed, and he had been a postdoc with a scientist named Erwin Mueller. Erwin Mueller had pioneered the development of something called a field ion microscope, and Alan Melmed had spent a postdoc position with him and learned that trade and become a very expert field ion microscopist, and had set up a system at NBS. So he came to me to see if we could provide some samples of this yttrium barium copper oxide to him. And so I gave him some of the samples which had been prepared by another scientist at NBS, a fellow named C.K. Chang. And C.K. Chang is very well known for having made the very first conducting polymer. He did this with Alan Heeger at the University of Pennsylvania, well before C.K. Chang came to NBS. And of course, Alan Heeger got the Nobel Prize for pioneering the development of conductive polymers. Anyway, C.K. Chang had made this superconductor. I gave pieces of that to Alan Melmed, but went up to work with him to try to make a sharp point. So you need a very sharp point to get any image in a field ion microscope in that microscope. And so you had to either electropolish to make a very, very sharp point, or some other method. And Allen was a real expert at doing this. Well, he wasn't real expert at making sharp points in these materials, it turns out, because he would think something was sharp enough, and we'd be working in his laboratory until late at night. I mean, 2 and 3 in the morning was common for us because it was such an exciting area. And 50 to 80 times, you put the tip into the microscope, pump out a vacuum, impose this very large voltage to ionize the gas that's around the tip, and thereby propel it to a phosphor screen to get an image of the location of these atoms. And the tip would fly apart. And so we'd start from scratch again, find another piece, try it out, destroy it. Finally, we got an image, and the image was just amazing. So this is a tool which will give you information usually on crystal structure. And so you'll see usually a series of circles showing where there's a pole of some crystallographic orientation. Here, we didn't see that. Over the whole field of view, we saw basically parallel lines. Very unusual image, not been seen in any material before. So we concluded from this that only some of the atoms are being imaged in the structure of this yttrium barium copper oxide. And so we got together with this fellow in our mathematics laboratory who was very good at imaging, developing images, computationally analyzing images. And we calculated what sort of image we would get if we assumed only certain atoms did imaging. And we came out with the fact that we're only getting imaging. And so this appeared on the cover of Science magazine, this picture, this composite picture showing that you only got imaging from these particular planes in the crystal structure of the yttrium barium copper oxide, which form planes of copper and oxygen. And we were only getting images from that. So that was a really nice finding as well there. So that's how I got into superconductivity and the sorts of things that we quickly did. And then once we had done quickly, there were a bunch of other things that we also did that aren't quite as striking, but certainly very important in terms of flux pinning and where the flux goes and how it comes out of the lattice. But we decided to change after a couple of years working on these sort of things to kind of go back to what we were working on before. This was kind of like other people in the community. After they had also done the things that they could do quickly, they started meandering back to the things that they were working on before.
Fantastic. So Bob, your work on high temperature superconductors had some significant outcomes. At what point did you get back to that thin film work you were talking about before? Did you find this as a small segue from what you were doing, or was this a major thing that you continued to do for many years?
Well, no, actually, after I was kind of like, I think most other people around the world, we stopped pretty much everything we were doing at that discovery in 1987, and worked on superconductors using the equipment we had at our disposal and our expertise. And so after a couple of years, we had pretty much done the quick things that we could do, and recognized that further exploring of the area would take a lot longer. That is, to answer some of the really important questions regarding keeping the current carrying capacity very, very high in some of these high temperature superconductors. And that was going to require a much more lengthy process. And we weren't particularly expert, I wouldn't say, in that area. So we kind of went back to what we were working on before, which is basically on thin film material, and specifically particulate materials that we would make by thin film processes like sputtering or co-sputtering in our case, primarily a ferromagnetic material and a non-ferromagnetic material like iron and silica is a good example of the systems we were looking at. So this is like 1989, 1990 time frame. And interestingly enough, during the high temperature superconductor craze of everybody, somewhat hidden was a paper, a couple of papers that were published by one by Albert Ferret in France, another by Peter Grunberg in Germany. And both of them had found an unusual effect in some thin films, and specifically layered material, where they had one layer on top of another. And specifically, if there were three layers, the two outer layers of which were a ferromagnet, and these are thin films, and the in-between layers, sandwiched between that, was a non-ferromagnetic material. They first looked at iron and chromium around room temperature, where chromium is essentially paramagnetic, so therefore not ferromagnetic. Obviously, the iron is ferromagnetic. And when that thickness of that chromium layer was very, very thin in the nanometer regime, they found an unusual effect on the resistance, electrical resistance of that material. In fact, the electrical resistivity of that sandwich structure was quite high when you applied, high, and when you applied a magnetic field, you got an even higher resistance, and it was quite a large increase in resistance. So this well-known magnetoresistance that was created in this particular nanostructure was on the order of perhaps 30 to 80%, depending upon what temperature people were measuring it at. Now, to put this into context, the largest magnetoresistance of any material known at that time was in permalloy. This is an iron-nickel alloy, and there it's on the order of 3%. So getting order one and almost 2 orders of magnitude larger resistance by applying a magnetic field was quite exciting. But most people missed this because they were all focused on the high temperature superconductors, including us. It wasn't until after we went back to what we were doing before, in particular, our focus was making these particulate magnetic films for recording media, high density recording media. If you could make the ferromagnetic regions down in the nanometer size range, then you could achieve many, many more of these in a certain square area of your hard disk or your tape if you're using tape, to store magnetically the information into ones and zeros, binary encoding. But if you make that little region or those particles very, very small that you're storing this information in, then you also need to have a more sensitive device to detect these magnetizations of ups and downs or rights and lefts, depending upon how you're magnetizing those local regions. And this discovery of this so-called giant magnetoresistance effect by Ferret and Grunberg independently showed a direction for making a very, very sensitive detector, because that magnetoresistance would drop relatively quickly as you applied a magnetic field to it. And you could use that signature to tell you which direction the magnetization of this material was very sensitively. And so the read heads on these hard disks basically were, people started to work on making them with a magnetoresistance detector, basically, so you could read these smaller regions. Well, that required, as I mentioned, a very nano-structured region. And about the same time, there was also a nice paper by another scientist in Germany, Gisela Herzer, who showed that with very fine particulate materials which had grain sizes in them that were in the nanometer regime, that you could get very, very soft ferromagnetic character in them. Now that's quite unusual. Normally, as you make things, the grain size smaller, the grain boundaries in the material impede the motion of domain walls, and therefore the material gets what we call magnetically harder as you get smaller and smaller grain size, because you have more and more grain boundaries to do this pinning. Well, Herzer showed that if you can make your crystalline grains very, very small, down into the nanometer regime, then in fact the magnetic coercivity, or that's the signature of whether it's soft or hard. You want a very low coercivity for a nice soft ferromagnet, like we use in a transformer core. Then he showed that that coercivity would drop, and drop very quickly as a function of grain size. And so this showed a new direction for making very good ferromagnets for things like transformer cores and that sort of thing. And that's where there's an awful lot of energy wasted throughout the world in transformer cores. So this was exciting. Again, a nanometer size is required here, in this case, grain size. And then around the same time, and I guess it was 91, there was also another paper, a theoretical paper by a couple of scientists, also in Germany, Neller and Hawig, and they showed that one way to make a better hard ferromagnet, that is, make the coercivities larger, was to use something they coined as exchange spring type of material, where you sandwich a very hard ferromagnet, something like these rare earth neodymium iron boron magnets, so it has a very big coercivity, sandwich a very thin portion of that next to a very soft ferromagnet, and then another hard ferromagnet next to it and soft. So again, layer, but with the thicknesses of these layers again being very thin, so that the magnetic exchange interaction between spins in one type of material are interacting with those in the other, then you could get actually materials with a larger coercivity and a higher saturation magnetization than you could if you just had a regular hard ferromagnet. And again, this pointed the direction for material development to make much, much better hard ferromagnets, again requiring this nanometer kind of structure. So this got me kind of involved in doing more of work in this nanometer regime. And I started organizing lots of conferences in this area, primarily at TMS meetings, but also at some MRS meetings and the Federation of European Materials Society meetings. And this brought me into contact with other people in other disciplines other than the magnetic regime, where it became obvious that there were interesting new properties of other types, optical, thermal, type structural properties of materials which had this nanometer dimensionality built into the structure.
This is it sounds a lot like the early days of what became nanoscience and nanotechnology. I mean, this is the early 90s, and people weren't talking about that too much until maybe the mid 90s as its own kind of area. I know that you got involved in what became the kind of build up to the National Nanotechnology Initiative. Is this the beginning of that?
Exactly. So after I got involved in organizing all these meetings and meeting all these different people from different disciplines of my own, it became obvious that this was an area of material science that really had not been explored in the past. But first of all, because people didn't really have the capabilities to controllably make these sorts of materials. But now that capability was available for all these scientists all around the world. And so, in fact, Actimet, the journal, recognized this as well. And so in 1990, they held this, this meeting on the topic. It was called Conference on Ultrafine Microstructure Materials. And this was in Atlantic City. And it was a relatively small meeting, but it brought together all these people from these very, very disparate fields to interact and to talk about the unusual things that were being discovered. And that was really, I would say, the beginning of this whole activity, because that then prompted a sequel meeting, which happened a couple of years later, which was held in Cancun, Mexico, organized by a scientist, Miguel Yacaman, who subsequently became the head of the Mexican National Science Foundation, essentially, later on. Anyway, Miguel organized the sequel meeting, and that started a whole series of international conferences on, now we called it nanostructured material. That is, materials which had some nanometer dimensionality or sizes in their structure, and examine this whole area. Well, that then prompted some of the government funding agencies in the US to be thinking, well, maybe we should be putting some money into supporting this sort of activity, especially when some of us would, in our connections with some of these agency people, indicated that much of this technology was being developed outside the US, and unless the US starts putting a fair amount of money into exploring this area, the US is going to lose out in the technology and its applications. And it was more the latter aspect that really made an impact on these funding agencies. And so Mike Rocco at the National Science Foundation, whom I had met in one of my organization of meetings, was talking to me one day about this, or vice versa, and suggested that we try to put together a major funding initiative in the US in this area. And so I helped him form this committee called the Interagency Working Group on Nanotechnology, which became a subcommittee of the Office of Science and Technology Policy out of the White House, the Committee of Technology. And basically, using the people I had come across and met in all these different agencies that had some interest in this area, I suggested a number of names to Mike Rocco, especially DOE people and people in the defense were the primary entities, as well as some here. Mike already knew the NSF people interested, and so we put together this committee and started meeting. The first thing we decided is that we needed to get some money to form a research that is exploratory panel to assess the state of knowledge in this whole area around the country, including the US. And so we did that. We had Dick Siegel from RPI as one of the chairs of this panel. And I forget the lady from University of California in Santa Barbara, who is in the electronics area as a co-chair. And so for the next couple of years, they were going around to different countries, holding meetings with scientists who are doing work in these areas and laying the groundwork for putting it together an initiative. At this, after this this review was performed, then those of us on this IWGN committee then began writing up a major initiative, and that was submitted to Congress in 1999, near the end of it. And President Clinton at that time saw its potential and backed it in showing his initial backing with an announcement at Caltech in January of 2000. And then, of course, much of our behind the scenes activity was also devoted towards selling this whole idea to members of Congress. Now, I can't sell it to them because that's against the law for a federal employee to do that, but I could provide information to them. So when they would come to me, I could provide it, or I helped put together the reports that others were supplying to members of Congress. And there was a very important person, Tom Khalil, on this committee. He was a consultant for the White House, and he came up, he knew the political scene quite well. And if Mike Rocco had not been the chairman of this whole committee and really knew who to go to other agencies, and selling and staff on it, and in addition, Tom Khalil, it probably would not have gone as well as it did. But Tom Khalil came up with the idea we got to have these grand challenges. What are we going to solve with this whole focus? And so we came up with these 10 grand challenges, which could excite the imagination of the general public and thereby members of Congress to vote for this. And so indeed the initiative did go through in 2000, and it's still continuing to this day. But the interesting thing about this whole activity, it was very frustrating at times because it was either on at one time, then it was off, and then it was on, then it was off, depending upon what sort of hearing was being held and who was backing it, who was not. But the one interesting thing I never even thought about, and I probably should have if I was smart enough, that was outside, after this initiative came out from the US government, putting a lot of money behind researching nanotechnology, outside the US, a lot of other countries did the same thing. And the reason was these other countries are always all looking at the US. And if they see the US putting a lot of backing and money into one area, they figured it must be a good area. And so therefore, they put together their own initiatives within their own countries to support research in their own countries so they don't lose out later on. And so much more money was put into this whole area around the world than was put into it in the US national initiative. So that was kind of an interesting finding that, as I say, I didn't know before. So, but anyway, but while this was all, so this was how the initiative got started. And I basically told Mike Rocco that I was, my position on this committee was not so knowledgeable in the political scene, but I would be the practicing scientist to bounce things off of as to whether something is a viable thought or not. So that was kind of my role I played in it. And so
all the way through the whole process.
Excuse me?
All the way through the whole process, you were playing that role.
I stayed on this committee all the way through the process, and then for a number of years after the first initiative, and it was renewed several more times up till now. So I kind of bowed out of this committee probably in probably 2005. Maybe 2010 probably is when I stopped active. I mean, we would hold meetings in the old executive office building pretty much every month, once a month, wow. And all of us would get together and decide what's the next step, et cetera. And then we began assigning putting together focus groups. And obviously being an employee at NIST, where our focus is on metrology or how to measure things. I was very active in the committee on establishing facilities that could address and make measurements at this size, materials with this size scale.
Yeah, it's right around this time. So you probably don't remember this, but I remember the first time I met you, Bob. That was during this kind of mid to late 90s period. And you came over to the University of Pittsburgh and you gave a seminar. And
I remember that.
I attended that seminar, and the topic of that seminar was nanoscience and nanotechnology, and some of the things you just talked about now were topics in there. And I was working on that for my graduate work. But you also had a connection to the magnetocaloric effect in there. I think it was right around that time that you were starting to work on something that I had never heard of before. And I'm not sure if you're ready to talk about this yet, but I know this is a topic that you worked on well into the 21st century. And, how did you get started on that? What was the connection to what you were doing before? And are you ready to talk about that?
Yeah, certainly. I remember giving that talk, and I hope I didn't yell at you for creating.
You didn't know me well enough.
At the lecture. At any rate, yeah. So around the same time that I'm helping put together this national initiative, as I mentioned, I'm still very active in my own research, but I started looking at other properties, specifically magnetic properties, that of course be my expertise, that could be affected by this nanometer structure. And it just so happened I was talking to another scientist at NIST. Actually, he was more of an administrator at NIST who had just joined one of the other divisions. He had been working at the Oak Ridge National Laboratory beforehand, and left there obviously and came to NIST. And I was talking to him about what sort of activities were going on there, and he mentioned, knowing that I was a magnetics person, mentioned this work on magnetic cooling. And I had not heard about this topic either. So this would have been 1990 probably, time period. And so I started thinking about that, did a little bit of reading what the magnetocaloric effect was upon which magnetic cooling was based. And I realized that there are two different types of materials people were looking into and researching for obtaining large magnetocaloric effects in order to have large cooling capabilities. And those two types of materials were ferromagnets near their Curie temperature and paramagnets, especially for very low temperature cooling. And this is where it was already being applied for low temperature cooling materials in order to get to the lowest temperatures possible. This whole idea of adiabatic demagnetization, for which a Nobel Prize was awarded back in the 1940s, I think, is where you cool down a paramagnetic material as cold as you can. So you get it down to liquid helium temperature and then pump on the liquid helium and get it down to about 1.6 degrees Kelvin. In order to get down even further in temperature, then what you would do is you do this cooling in a magnetic field in the presence of one of these paramagnetic salts, this case, and then you take the field off, and that would cause it to cool down into the millidegree temperature regime. But I realized that if you looked at some other types of magnetic materials, specifically materials which are called superparamagnetic, then you actually get some advantage in this cooling capability at low magnetic fields. Because the other problem that always seemed to me was problematic with this technology is you'd have to use a very large magnet, a big superconducting magnet, to get a large enough field to affect significant cooling capabilities. So you need to reduce the field somehow.
Can you describe what a superparamagnetic material is? Is it a supermagnet?
So no, okay. So a superparamagnetic material is a material kind of like what I was working on making at this time. These composites of materials where you have regions of ferromagnetic clusters that are dispersed in your material, and they're independent of each other. But within any one magnetic cluster, all the magnetic spins are all lined up in one direction. So now you come around with a big magnetic field from outside, and you can rotate the direction of magnetization of these clusters to try to line with the field. And you get, since the magnetic moment of this cluster is the magnetic moment on a single atom times the number of such atoms, because the spins are all lined up in this ferromagnetic cluster, then the magnetic moment is very much larger than that of a single spin.
How big are these clusters, Bob?
So they could be hundreds to thousands of spins. So they can be quite large depending upon the size of the little clustered regions you make. And so, but when you take a magnetic field off of this sort of system, then the spins of these big clusters, the overall total spins, randomize in random directions, just like a paramagnet does with individual atomic spins. With these superparamagnet, you have these clusters of spins which orient at random with no magnetic field around them. And so there's no remaining magnetization when in this material when the field is off. But when you apply a field, you get much, much larger magnetization chains because so many of these spins in the clusters reorient right away. So we put together a theory that you could get this in very much in what we call enhanced magnetocaloric effect in we call them nanocomposites because they were nanometer sized clusters in kind of a sea of material which was not ferromagnetic at all. And we showed that if you, for certain low fields in particular, indeed the magnetocaloric effect you would get from such a system was much, much larger than that of a normal paramagnetic material. And then we subsequently showed this in a garnet, specifically gadolinium gallium garnet. And by the way, gadolinium gallium garnet was one of the best magnetic refrigerants. It's paramagnetic material, best refrigerant down to about 15, from about 15 degrees Kelvin and down to lower temperatures. And that's why we chose this material. And we then measured it directly by measuring how much we had a thermocouple embedded in a canister, going back to my days at Caltech where I was designing a system for measuring heat capacity. It's the same sort of system. And we also then measured it by magnetization measurements and showed that they were consistent with each other. And showed, in fact, if you took a little bit of iron, this is our contribution, if we put a little bit of iron into this gadolinium gallium garnet, then the iron, the magnetic spins in the iron would couple to neighboring gadolinium spins, getting so that if you change the orientation of one of those gadolinium spins, the iron atom would feel a torque rotating it, and that would exert another force on another neighboring gadolinium spin, causing it to also rotate with it, thereby forming a magnetic cluster. And we showed, we showed that indeed made the material superparamagnetic, and we got this enhanced magnetocaloric effect in the system. And that kind of opened up a new area. So this was in the early 1990s, the same time I'm involved in these the NNI activity. So around 1997, I think 1998, there was a paper that was put out by the people at Ames, Iowa, Ames Research Lab, showing what they call a giant magnetocaloric effect in a gadolinium germanium silicide. And one of the things we showed right away is this material gets its large effect because it has a field-assisted crystallographic change. So if you apply a magnetic field to it, it causes the crystal structure to change. And when it changes, then its magnetic character changed to become more ferromagnetic at that point. And so you've got a big enhanced effect here. And what we then subsequently showed is if you, again, going back to our earlier activity, we thought, well, let's see what happens if we put a little bit of iron into it, just like we had done with this garnet material. And one thing we found is that, in fact, the peak effect, at this time, the figure of merit people were using was how much entropy do you get by aligning these spins? See, this magnetocaloric effect comes about from basically aligning magnetic spins in a field, thereby ordering them in some order, whereas before they're somewhat randomly oriented and there's no magnetic order. So if you can order them, then that means that you can reduce their entropy. That is the spin entropy in the system. Spin entropy, of course, being a measure of disorder. And so if you can order these spins, then you can decrease their entropy, and that can be converted to a temperature change depending upon the heat capacity of that material. Well, we found that indeed, so this amount of entropy varies with the particular temperature over which the material happens to be. And so what we found is that with this gadolinium germanium silicide with a little bit of iron in it, that peak entropy term actually dropped by a factor to about 1/3 of that if you had no iron in it at all. So using the existing metric of deciding whether this material is good or not, you would automatically think, well, this new material with the iron is terrible. You don't want to use this at all. But at the same time as it dropped this peak term, it also had no magnetic hysteresis in it. If you went through a field cycle, which is what you're going to do on any magnetic refrigerator, you're going to go through a field cycle of the refrigerant, it has built in to that material some sort of magnetic hysteresis. And that's the amount of energy cost in going through this field cycle. And so you want that to be as small as possible. Well, it just so happens that the gadolinium germanium silicide has very large hysteretic effects, but with this iron had very small. So if now you take the peak entropy and integrate that over the total temperature range you're going to operate your refrigerator at, coming up with something called a refrigerant capacity. And if you then subtract out of that the amount of work to go through a field cycle, when we come up with this modified refrigerant capacity, because you're taking out the major magnetic work, we compared that to the two materials, we find that that material with the iron added is so much better, in fact, by a factor of 2 over this gadolinium germanium silicide with no iron in it. So anyway, and those are the two major things I think we did in that area, and that was I think we came out with our papers in that around the beginning parts of the 2000s, maybe 2003, 2004, somewhere around there. During the same time, we were also working on other projects, which turned out even, in some respects, as exciting as this magnetic cooling area. Again, in the 1990s, we had this guest scientist come to our lab from Russia. Now, this, of course, is during the time as the USSR has broken up, and there are all these scientists in Russia who aren't getting paid. There's no money to support their activities, and so this one scientist, Valerian Nikotenko, came to our laboratory and had this idea for, initially it was for imaging magnetic flux penetration through superconductors. Of course, this is that same time period where the high TC activity was going on, although it's starting to die away a little bit. And so the idea was to use a thin film of a material that he would put on top of a sample, and then he would apply a magnetic field perpendicular to that sample. And this film had the property on top that it was in plane magnetized. Now, when the field went through the sample, say one of these high temperature superconductors, went through it and into the film, through the film on top, as long as it was not superconducting below. If it was superconducting, the flux get expelled outside of it, it would not come right through. So if it came through, then the magnetization in that film would rotate perpendicularly. And now if you came down with a light beam from the top that was polarized, so its electric field vector is in one direction, then it would see this perpendicular magnetization region if flux actually penetrated the superconductor underneath it, and it would rotate the polarization of this light beam. So when it got reflected back up to your microscope or eye, you could see a color change in that local region. And so basically it became a really nice technique for imaging, getting images of flux lines which had penetrated the superconductor. And it was very useful in showing how flux came in and where it got stuck and how it came out. It was wonderful. But when he came to me a little bit after that initial work, he suggested that we might want to modify that technique and try to put this thin film on a ferromagnet, recognizing that especially thin film ferromagnets will tend to be magnetized in the plane of that film. And so if any of those magnetic spins in that sample rotated upwards, if you had this thin imaging film on top, you could detect that. And so that's was this idea of Valerian Nikotenko, and we decided we would put together a system and test that. So we did that, and it turned out to work wonderfully. So one place where you get magnetic spins coming out of the sample plane is when you have a domain wall in your sample. So half of it is magnetized this way, other half of it's magnetized this way, still being in the plane. But at the boundary, you get some magnetic flux lines coming out of the plane. And if you had this imaging film on top, then it would rotate its magnetization vector perpendicular, and you'd be able to see it and get actual pictures of it. So we realized that this was a pretty important technique for detecting domain walls and seeing how they move. We could measure their dynamics, and so we applied it to some interesting nano materials. Specifically, materials which were kind of like the materials I did my PhD thesis work on, where we were looking at, if you recall, these mictomagnets, which were clustered material, but where there are both ferromagnetic and antiferromagnetic interactions working on individual spins. Well, one of the signatures of that material is you get a hysteresis loop, which is displaced along the field axis. And in fact, if you just take a thin film of a ferromagnet and put an antiferromagnet on top or vice versa, then you get the same sort of magnetic hysteresis loop. If you cool the material down through from above the nail point of the antiferromagnet to below it, and then measure it down there, you see this displaced hysteresis loop. So my thought was, well, let's use this imaging technique of ours to explore that. And in fact, that's what we did. We got this nice thin film of a nickel oxide, an antiferromagnet with a permalloy, a nice ferromagnet at room temperature on top of it. And we did some imaging, and we, first of all, we measured the hysteresis loop of it, and sure enough, it's nicely displaced. And we showed that, in fact, in going from positive fields towards the side of negative fields where it shifted towards negative fields, then in fact, the switching from positive magnetization and negative magnetization occurred by the nucleation of local regions which were magnetized opposite most of the material, which is a normal method for reversal. And those then, but they would nucleate on the edges of the sample where there are surface perturbations. That's a normal process, and they'll propagate through the rest of the material. But what was really interesting or unusual is when you came back with the field and you came reduce it from the negative direction to 0 and then slightly positive, then indeed you got nucleation of reverse direction domains in material, but they were located not on the edge of the sample, but they were located inside the sample, kind of along lines. They are along screw dislocations and along edge dislocations in the material. And that's where we realized that it's so much better to be lucky than smart, because these samples that Alison Chaikin from the Lawrence Livermore National Lab, she had prepared these samples for us and had deposited them on magnesium oxide single crystals. In order to get more samples for different types of measurements, she took this magnesium oxide before doing the deposition and cleaved them into smaller pieces. Well, interestingly enough, when you cleave the magnesium oxide, you actually put in dislocations into the magnesium oxide. And that's what we were seeing. So when she then grew these films on top, this dislocation, like an edge dislocation in the magnesium oxide, propagated into the nickel oxide first, and then the permalloy was on top. And the idea here is when you have a dislocation in this antiferromagnet, initially the spins are alternating in the antiferromagnet. You put a dislocation to it, now you're going to have spins along that dislocation which are lined up. And imagine the effect of that on a neighboring ferromagnetic spin in that ferromagnet. It doesn't know which way to go, so it's easiest for those to begin turning than spins which are way out here away from that edge dislocation. And that basically showed us that that one of the reasons, one of the big uncertainties in this whole area was how come it took so much smaller fields to get this reversal in such systems than had been predicted. It's all because of dislocations which people weren't controlling in their material. And that's normal, because it's very hard to control them. So anyway, that showed the real power of this technique. And then we applied it to an exchange spring of the type I mentioned that Miller and Hawig had predicted for getting very good hard ferromagnets. And here we showed that in a film, in this particular case, it was samarium, cobalt, and iron, as I recall, that had been prepared at Argonne Laboratory by Sam Bader. And what we had a thin film of samarium, cobalt, and then a thin layer of iron on top of it. And then we looked at the magnetization reversal in this imaging tool, which is called the magneto-optic indicator film technique, or MOIF, M-O-I-F, by its acronym. And what we showed is that, first of all, when we tried imaging it, we didn't see anything. We couldn't see any domains. That's because the domain walls are not on the top, they're on the edges, because you have basically a hard ferromagnet, a soft ferromagnet, so the domain wall is between them. So we wouldn't see anything. So in order to decide how reversal occurred, we drilled a little hole in our sample, and from the inside edge of that hole, one half of it would be light colored, the other half would be dark colored, and that mimics the direction of magnetization in the region surrounding that hole. And we showed that if the field was slightly off the easy axis of magnetization, these spins in the soft ferromagnet rotated in one direction. And if the field was slightly off in the other direction from the easy axis, the spins rotated in the opposite direction, thereby confirming Miller-Hawley's theory directly. So that has turned out to be a very, very powerful tool, and we've applied it to lots of other things since then. But it's a extremely valuable technique.
Very interesting, Bob. This is a great tool for so not only the science that's coming out of it, but the tool is important too.
Exactly, exactly.